Hey, calculus students. We are studying our IB topics, and we're in the middle of topic 1. Today we're going to focus on sections 1.5 and 1.7 in our subject outline or syllabus outline, which is logarithms. So we're just going to go over some of our basic log skills, and I am going to reference a reference sheet that I've made for you guys that you should have received. This includes a lot of our log properties, including a log base b of b being equal to 1, log base b of 1 equaling 0, log base b of b to the x equals x, b to the log base b of x equals x. These properties apply when there is a base 10. Remember, with a base 10, you're not going to see a base written in there. A log base 10 is implied when there's no base written. And then these will also apply to natural log, which are logs with a base e. So when you see an ln, that is an implied log base e. Below that, you'll see our product, our quotient, and our power rule. Below that, we have options for solving log equations. And below that, options to solving exponential equations. At the very bottom of your reference sheet are just a reminder of what the exponential parent function looks like and what the exponential log function looks like, and then e to the x and ln of x. This really falls under topic 2, which is functions, but it's in the log family, so I thought I'd include it on the same reference sheet for you. And then at the very top, is just the reminder that log form and exponential form are two forms of representing the same relationship. And when you switch back and forth, the base is the same. So the base of your log becomes the base of your exponent. Hop across the equal sign for your x, that becomes your power. And then it isolates the log argument. So you have equals x on the other side. Or if you're going the other way, if you're starting with exponential form, the base of your power becomes the base of your log. Hop across the equal sign for the log argument, and then it isolates your exponent, which is x. Okay, so for example number 1, in our notes, we're being asked to switch between log and exponential form. So this is an exponential. So my base is 49, so I'm going to have log base 49. I'm going to hop across the equal sign for my log argument, and that equals my power of 1/2. If we are working with a log expression and asked to switch to exponential form, you start with the base. So the log base is 6. You're going to hop across the equal sign to grab your power. So 6 to the negative 1 power equals the log argument, which is 1/6. All right, the next section is illustrating those log properties that were in the box on your log reference sheet. And so we're just looking for examples of these 4 properties. So when you have log base 7 of 7 to the 9, when the base of the log and the base of that argument match, that simplifies all the way down to the 9. There is an implied base e in here, so you have a base e and an exponent base e that match, so that will simplify all the way down to -3. When you have a base to a log with the same base, those simplify down to that log argument, which is 5. And then here, it might not look like they have the same base, but when there isn't a base, it's an implied base 10. So the 10 log base 10 of 8 simplifies all the way down to 8. If you look at letter E, these do not have the same base. However, we can write it with the same base. So 64 can be written as 4 cubed. And then this simplifies, when these bases match, that simplifies all the way down to your exponent of 3. For log base 2 of 1/8, I'm going to do that in 2 steps. So the first thing I'm going to do is rewrite the 8 as a 2 cubed. And then I am going to bring that 2 up to the top, so it becomes 2 to the -3. And then my bases match, so this simplifies all the way down to -3. ln of 1 is always equivalent to 0, and people forget that all the time, but think about that. That is saying a log with a base e of 1 equals something. Log with a base e of 1 equals something. That's saying e to what power equals 1? Well, e is 2.7-ish. If you raise 2.7 to a power, the only way you're going to get a 1 is if your power is 0. Hence, ln of 1 is 0, log of 1 is 0, log base 2 of 1 is 0. And then on this last one, log base 81 of 9. Now, if you realize that you can rewrite 9 as an 81 to the 1/2, that's probably the fastest way to work this. So the square root of 81 is 9, and then that simplifies all the way down to a 1/2. But there is another way that you can work this one. So let's say I were to work the same exact problem. I could set an x on the other side, and you can switch forms. So you would have an 81 as your base. You're raising it to the x power, and that equals 9. And you can rewrite 81 as 9 to the second power. And then 9 to the 2x equals 9 to the 1. And once your bases match, your exponents match. Now, if this isn't looking familiar, since it's been a long time, you're actually going to see this later on down at the bottom. Question number 6. But I just wanted to show you that there's really two ways to work this. One way is to force it into an equation and solve it. Or if you recognize 9 as 81 to the 1/2, that is the fastest way to work it. Okay, when you are asked to expand an expression, they want you to separate all of these variables so that you have separate log expressions. We're using these 3 rules in the middle. So your product rule, your quotient rule, and your power rule. So when you have your product rule, the log of a product is equivalent to log of m plus log of n, and it works the other way around. So if you had a sum of logs, you can combine them by creating a product of those log arguments. For your quotient rule, if you have a quotient, you can separate that by creating a difference. Please be certain that the expression that is in the denominator must have the subtraction symbol in front of it. And that works the other way around. If you have log of m minus log of n, if you have a difference, you can combine that by creating a quotient where the n has to be in the denominator. And then the last rule is our power rule. So if you have a log base b of m to the p, you can take this p, scoot it out to the front, and it becomes a coefficient, or the other way around, you can pull the p up as an exponent. So the first thing I'm going to do here is I'm going to separate out my numerator and my denominator. So I have log of x to the 4th, y squared, z to the 7th, minus log of w cubed, p to the 5th. And now I have a product here, so I'm going to separate each of those as a separate log expression. So log of x to the 4th plus log of y squared plus log of z to the 7th. And when you have a product in your log argument, you separate that with 3 separate log expressions, but each one needs to have the same exact base as the original, which is a base 10. For the second expression, this is a quotient, but what I'm realizing is that when you have a when you create your expression here, it was a quotient to begin with. Every expression that was in the denominator is going to wind up with a subtraction symbol in front of it. So you can do this one of 2 ways. If you treat this as like a multiplier in front, the subtraction symbol, I am going to treat this like a product. So that would become log of w cubed plus log of p to the 5th. However, when I distribute the subtraction symbol, they're both going to become subtracted expressions, which marries up with what I was expecting. Any expression or variable sitting in the denominator needs to have a subtraction symbol in front of it. And we're going to go one more step, and every power is going to be brought out to the front. So 4 log of x plus 2 log of y plus 7 log of z minus 3 log of w minus 5 log of p. And there is your log expanded expression. Next example is one that is expanded and when you want to consolidate it. In order to consolidate, if you look back at your rules, when you're consolidating, the bases have to be the same and the coefficients need to be at 1. So in this example, we have coefficients. So I want to pull those coefficients up as a power. So I'm going to have log base 4 of 4 cubed minus log base 4 of 16 to the 1/2 plus log base 4 of 3 squared. If you'd like to go ahead and simplify those, you certainly can. So 4 cubed is 64. 16 to the 1/2 is square root of 16, which is 4. 3 squared is 9. And now I'm going to combine these. And when you combine these, we're all combining them into one big log expression. The expression that has the subtraction symbol in front of it, that argument needs to go in your denominator. So there's your 4, which means on the top you're going to have 64 times 9. So it doesn't matter what order these are written, it only matters what sign they have in front of them. The two positive expressions, those arguments are going to go in the numerator. All right, so we're going to clean this up a little bit. So 4 goes into 64 16 times. And that simplifies all the way down to log base 4 of, I think that's 144. All right, your change of base formula allows you to take any base and rewrite it using a base 10 and a base e. So if you wanted to rewrite log base 3 of 4, that would become log base 10 of 4 over log base 10 of 3. So the log argument goes on top, the log of the base goes on the bottom, and you give it any base that you want. And obviously, if it's a base 10, you do not need to write the base 10. So you'd have log of 4 over log of 3. If you were trying to rewrite that expression with an base e, that's a log base e of 4 over a log base e of 3. And obviously, a log base e is really an ln. So ln of 4 over ln of 3. I would not normally write that step. I would just hop straight to my answer on that. All right, let's get into solving exponential equations. So when you are solving an equation, there are several different versions of problems you may be presented with. This would be an example that you'd see on a non-calculator test because these are both powers of 6. So you can rewrite 36 as a base 6. So what I'm going to do when I say I'm using like bases, let's go back to our reference sheet. Let's look at our options. Options to solving exponential equations. You can switch forms from exponential to log form. You can take the log or ln of both sides, but in this case, I really don't need to do either of those because I can rewrite 36 as 6 squared. And I'm just going to clean that up. We've got a power to a power. So I'm going to multiply 2 times 3x is 6x, 2 times negative 9 is negative 18. And once their bases are the same, their powers must be equivalent. That is because exponential functions are one-to-one functions. If the inputs are the same, the outputs will be the same. If the outputs are the same, the inputs will be the same. Every x corresponds to one y, every y corresponds to one x. So if my bases are the same, my powers must be the same. So I'm just going to set my exponents equal to each other. And I'm going to solve. So subtract my 2x, add my 18 over to the other side. And we've got 19 over 4. Okay, so we've seen an example of an exponential equation where they could be written with like bases. Let's take a look at an example where they cannot be written with like bases. So we've got something like example B. Now, I don't know yet if they can be written as like bases. If you have an exponential expression, you want to get that isolated first. So we're going to add 5 to both sides. And I'm now considering, can I write 20 as a base 2? No, you cannot. 2 to a power would never equal 20. So you're kind of stuck at this point. And so you have a couple of options. And so I'm going to go back to my reference sheet. And my reference sheet says, one of my options is I can switch forms from exponential to log. The other is I can take the log of both sides. So if I switch forms, I'd have a log base 2 of 20 equals 2x plus 1. That works. It's great. It's fast. The only dilemma with that is in IB, they tend to love to put inequalities in exponential problems. And when you switch forms with an inequality, it's very difficult to remember which way the inequality symbol faces. So in general, whether I'm working with an equation or an inequality, I take the log of both sides. And when I take the log, you can choose whatever base. I'm going to choose ln. So I'm going to have ln of 2 to the 2x plus 1 on this side. I'm going to have ln of 20 on this side. And I'm trying to isolate x. This whole expression here is a power, so I'm going to pull that power out to the front. That's our power rule. It's one of the reasons why we learn those rules, so that we could use them to solve equations. And at this point, you can either distribute the ln of 2, or I'm going to divide by ln of 2. So we have 2x plus 1 equals ln of 20 divided by ln of 2. I'm going to subtract 1 from both sides. And I'm going to divide by 2. I have a fraction over here, so instead I'm just going to multiply by 1/2. So I have x equals, and 1/2 times ln of 20 over ln of 2 would be ln of 20 over 2 ln of 2, and then minus 1/2. And there are several variations of how you could write this. So realize that, this is not the only correct version of this expression. All right, let's talk about solving log equations. And so when you're solving log equations, you have several options. But in this very first example, they both have a log base 10 with an argument. And so just like when you're working with like bases, we have log-like bases as well. And when the bases are the same, you can just set the 2 log arguments equal to each other. And then solve for x. So we would have 8x minus 8, add 8 to my other side. Let's come over here. We would have 7 over 8. Okay, so let's take a look at the next problem. Now, I don't see a log on each side. So when I have an equation with lots of terms, I'm going to get the log expression by itself first. So I'm going to subtract 3 from both sides. And then I'm going to divide both sides by -5. So I have log base 2 of x equals -5. And at this point, you're solving a log equation. So you've got a couple of options. Let's go back to our reference sheet. You could switch forms from log to exponential. You could set your log expressions equal to each other. That's actually what we did on example A. We set our log expressions equal to each other. That only works when you have a single log expression on both sides. And the last option is you can exponentiate both sides, meaning raise both sides up as a power using the same base. Well, in this example, the easiest thing would be just to switch forms. So I'm going to switch from log to exponential form. So my base of my log becomes my base of my power. So 2 gets raised to the -5 power, and it is equal to x. And then I'm going to just clean that up. So 2 to the -5 is 1 over 32. Okay, one last example. So we're solving the log expression by first consolidating log expressions. They're not going to tell you that on an IB problem. They're probably going to say just solve. You cannot set log expressions equal to each other because you have multiple log expressions on this side, and that's why we're going to combine them together. So we are going to use that product rule. Remember, the product rule says when you have a sum of logs, you can combine them as a product. So that would become x times x minus 7. And now, because I have log arguments, a single log expression on both sides, same base, and I have log arguments, I'm going to set x times x minus 7 equal to 18, just like we did earlier on example A. So x times x minus 7 equals 18. X squared minus 7x equals 18. And we're going to factor. So x minus 9 times x plus 2 equals 0. X equals 9. X equals -2. One thing we haven't talked about is logs have a natural domain. A log argument has to be greater than 0, always. So when you solve a log equation, let's grab our answers and substitute them back in. So if I substitute 9 in, log of 9, we're okay. That log argument has to be positive. It's positive. 9 minus 7, that gives me 2. That's positive. I'm okay. If I substitute a -2 in, though, log of -2, that is not a defined number. You're going to throw that example out. Okay, perfect timing. Thank you so much for listening. I wish you guys all the best with your logarithms. Thanks.